Hi, my name is Michal. I'm a postdoc at UC-Berkeley, and I will be talking about using the concept of isotropic position to accelerate discrete sampling. This is joint work with Nima Anari at Stanford University. Suppose that we are given oracle access to a distribution mu over subsets of size k from a ground set of n elements, and our goal is to generate approximate samples from mu. Many discrete sampling tasks can be reduced to this canonical form. And in many cases, the size n of the ground set is much larger than the size k of the sample set. So motivated by this, we ask, when can we sample from mu in time that is polynomial in the output size k? Of course, in general, this is impossible since we must observe all elements of the ground set to know where the distribution mass is concentrated. Yet we show that after some initial preprocessing, sampling in time polynomial in k is possible for a large class of discrete distributions. A useful analogy comes from the line of works studying sampling algorithms for continuous distributions. For example, random walks over a high-dimensional convex body. Here, the notion of isotropic position is central to many sampling algorithms. Intuitively, this condition ensures that all directions are equally as important when exploring the high-dimensional space, which is expressed by the target random variable having identity covariance matrix. In the simplest terms, to ensure that a random walk over a continuous distribution can be fast mixing, the density f should be in isotropic position as well as be a log-concave function, which we can interpret as being sufficiently well-behaved. In fact, often instead of requiring that the target density be isotropic, we can instead convert it to isotropic position, which can be done with a simple affine transformation. This high-level framework has proven highly effective in geometric random walk literature, and our goal is to develop an analogous framework for discrete distributions. The notion of isotropy, which we propose for discrete distributions over subsets, is in many ways analogous to its continuous variant, in the sense that it strives to ensure that all the elements in the ground set are equally important, which is represented by the condition that their marginal probability of inclusion must be the same or nearly the same. Also, like in the continuous case, if the marginal probabilities are known, then it is easy to convert the distribution to isotropic position. Here, the bars represent the marginals of mu. Now, suppose that we duplicate the elements of the ground set proportionally to their marginals. The induced distribution is equivalent to the original one, and it has uniform marginals, which makes it isotropic. Of course, the duplication is merely useful conceptually and can be avoided in the algorithms. With this notion of isotropy at hand, we can now present our main results. Informally, our first theorem states that given oracle access to a distribution mu that is nearly isotropic and has a log-concave generating polynomial, we can approximately sample from mu in time polynomial in the output size k. Here, we absorb logarithmic dependence on the approximation error. Having a log-concave generating polynomial can be thought of as a discrete analog of the log concavity for continuous distributions, as it ensures that the distribution is sufficiently well-behaved for polynomial time sampling to be possible. Our second theorem ensures that any mu with a log-concave generating polynomial can be efficiently converted to nearly isotropic position. Here, the complexity has to depend at least linearly on n. And we show that, in fact, almost linear dependence is sufficient. A generating polynomial of a discrete distribution is defined so that each monomial represents one possible outcome, and each variable corresponds to an element of the ground set. These polynomials have proven remarkably effective in studying discrete distributions. In particular, recent work has shown that the generating polynomial of many well-behaved distributions satisfies the standard log concavity condition shown here. Two major classes of such distributions are determinantal point processes, also known as volume sampling, and uniform distributions over Matroid bases. More specific examples include random spanning trees and forests, among others. Our framework can be applied in all of these cases, both to achieve accelerated sampling as well as for counting problems, such as estimating the partition function. Okay, let's discuss some prior work. Polynomial time sampling from distributions with a log-concave generating polynomial was established recently by Anari, Liu, Office-Garan, and Vincent. They showed that there is a random walk where each step takes order n time, and it mixes in order k log k steps, resulting in overall runtime of n times poly k. This walk is very simple, and we will call it the down-up walk. The state space of the walk is all of the subsets of size k. Starting from some subset, we first drop one of its elements uniformly at random. That's the down step. And then add a new element with probability proportional to mu. This is the up step. Clearly, the up step requires one pass over all the elements of the ground set, which is why the procedure must inevitably be at least linear in n. We will use the down-up walk in our algorithm, but we will show how the linear time in n can be avoided. As I mentioned, a major class of distributions with log-concave generating polynomials is called determinantal point processes, DPPs for short. And some of the ideas we used in this work were inspired by my earlier work on DPP sampling. Here, we represent the ground set as a collection of vectors, and our goal is to sample proportionally to the squared volume spanned by the selected vectors, which is why this is also sometimes called volume sampling. This class includes such distributions as random spanning trees, and it has been useful as a method for sampling diverse subsets in machine learning and statistics. DPPs have also proven instrumental in understanding the complexity of a number of tasks in randomized numerical linear algebra. For example, they were shown to be the optimal method for column-based matrix reconstruction, first shown by Deshpande, Rademacher, Vempala, and Wang. And in my work with Manfred Warmuth, we showed that a determinantal point process achieves the optimal label complexity of least squares regression. DPPs are also used as a randomized rounding technique to obtain relative error approximations in a class of combinatorial optimization tasks called optimal design. For an overview, you can check out our new survey. For sampling from DPPs, of particular relevance is a recent approach proposed by myself and then further improved together with Daniele Calandriello and Michal Valko. Here with a slightly different access model, which is a standard in this area, we show that a DPP can be converted to nearly isotropic position in n poly k log n time, and then we can sample from it exactly in just poly k time. The core idea behind this approach, called distortion-free intermediate sampling, is quite simple. We first draw an intermediate sample sigma to reduce the size of the ground set. When mu is isotropic, the intermediate sample can be almost uniformly random. Then we downsample according to mu restricted to the intermediate sample. The fact that we can implement distortion-free intermediate sampling and thereby obtain exact sampling relies on the special structure of DPPs, which allows for both exact sampling and exact computation of the partition function in polynomial time. Neither of these properties are satisfied by the general class of distributions with a log-concave generating polynomial. So this raises the question whether the intermediate sampling paradigm can still be extended to this class if we give up on the distortion-free aspect. We show that, in fact, it can by transforming intermediate sampling into an instantly mixing random walk. Here's what I mean. Suppose that S0 is a state in our state space consisting of subsets of size k. We now sample a large collection of the elements of the ground set. Think of this again as uniform sampling, and merge them with S0 to produce our intermediate sample sigma. Then we sample S1 from distribution mu restricted to sigma. By repeating this procedure with S1 instead of S0, we get a random walk in our state space. And it is easy to see that mu will be its stationary distribution. Moreover, we show that if mu is isotropic and the size of the intermediate sample at least of the order of k squared, then after just one step, this random walk gets to within 1/2 total variation distance of mu. And after log 1 over epsilon steps, it gets epsilon close. It remains to show how we can sample from the mu distribution restricted to the intermediate sample. For this, we can simply use the down-up walk discussed earlier, but run it locally on the intermediate sample. Since the size of the ground set for the down-up walk is now poly k, it will mix in poly k time. Overall, the procedure can be viewed as a two-level hierarchical walk with macro steps of the instantly mixing intermediate sampling walk combined with small steps of the local down-up walk. Or alternatively, we can think of this as the down-up walk performed on a periodically refreshed uniform sample of the ground set. Our proof techniques for showing that our intermediate sampling random walk mixes instantly rely on the notion of negative dependence. This property, in its most basic form, states that conditioning on one element ending up in the sampled set can only decrease the marginal probability of any other element. And as a result, the marginal probability of a small set T is upper bounded by the product of the marginals of its elements. This is satisfied by all determinantal point processes, but not by all distributions with a log-concave polynomial. However, for these distributions, we were able to show a somewhat weaker, nearly negative dependence, where the upper bound holds up to a multiplicative factor, which should be of independent interest. This is still not sufficient, however, to show instant mixing of the intermediate sampling random walk. Instead of bounding the marginal probability of a small set T of size less than k, we must instead bound the probability mass concentrated in a set T of size larger than k. Here, think of the set T as our intermediate sample. In fact, we can use the standard negative dependence to bound this probability, but this leads to suboptimal bounds. So it is necessary to reframe the notion of negative dependence. The natural representation of the sampled set S from the perspective of standard negative dependence is via n binary variables, which represent the inclusion of each element of the ground set in S. Another representation, which turns out to be more natural from the perspective of intermediate sampling, uses a sequence of k random variables, which represent the indices of the elements sampled by S. The sequence can be also defined simply as a random ordering of the elements of S. Our next result can be viewed as a negative dependence property with respect to this sequential representation of S, with the events defined by a set T of size at least k. A simple rewriting of both sides of this inequality shows that this is in fact a bound on the probability that the sampled set S is contained in T. To prove this, we use modified log-Sobolev inequalities developed recently by Krayan, Guo, and Moussa. Intuitively, this result ensures that no choice of intermediate sample contains too much probability mass of mu, and so a uniformly random choice will be sufficient. To complete our main results, we must show how to convert any distribution with a log-concave generating polynomial to nearly isotropic position. In fact, as I mentioned earlier, all we need to do is to estimate the marginal probabilities of each element of the ground set. Naturally, this can be done in polynomial time via repeated sampling, relying on the down-up random walk, which does not require isotropic position. However, this naive approach results in a quadratic dependence on n, because both the number of samples and the cost of sampling are linear in n. In avoiding this, our goal is to take advantage of our accelerated sampler even before we find the isotropic position for mu. Our strategy is to define a cooling schedule, which consists of intermediate distributions that are gradually transformed into mu. We start with nearly point mass distribution, for which the marginals can be trivially estimated. And so we can use our poly K sampler. As the distribution is gradually transformed, we keep updating our marginal estimates so that they always remain sufficiently accurate for the accelerated sampler to work until we finally end up at mu. We show that poly K log n cooling steps is sufficient. And as a result, the overall cost of estimating the marginals becomes nearly linear in n instead of quadratic. I will conclude with an example application of our results, showing that we can count bases of a rank K matroid to epsilon relative error in n plus 1 over epsilon squared time, up to a poly K log n factor. This is as opposed to n over epsilon squared cost using previous samples, which means that in time nearly linear in n, we can obtain a root n relative error approximation. Overall, we showed that it is possible to sample from a wide range of discrete distributions in time polynomial in the output size, which, among other things, enables high precision counting for many tasks. Our approach demonstrates that isotropy is a useful concept not only for continuous, but also for discrete distributions, and should be of broader interest. In terms of open questions, we ask, what is the optimal dependence on K? In particular, our analysis requires that the intermediate sample be of size at least K squared. However, the proposed algorithm may still be effective for much smaller sizes. Also, it seems likely that isotropy can be used to accelerate sampling even for distributions without a log-concave generating polynomial. Possibly one approach of extending our framework is to take advantage of higher order marginals to define more elaborate notions of isotropy. Here's a complete list of references. And thank you for your attention.